Chapter 8 was called Molecules in Action, and it was the last chapter that we looked at in Unit 2, Smells, and it was an attempt to introduce one more concept, which was polarity, to tie it into our hypothesis for the molecules that smell and the molecules that don't smell. So we're going to walk through the chapter. The first lab activity we did, there were stations set up around the room with different liquids in burettes, and you had a charged wand, right? You charged it by rubbing it with the rabbit fur, and then you put the wand next to each of the liquids, and you saw that some of them bent, and some of them had no effect. The other thing you tried was putting a drop of each liquid onto wax paper, and some of the liquids formed a nice bead, and some of them just formed a little flat puddle. After we did the activity, we related it to what we called the polarity of the molecule. Polar molecules have charges on either end of the molecule, specifically one end of the molecule being more positive and one end of the molecule being more negative. That's what it means for a molecule to be polar. It's that it has one side that's positive and one side that's negative. Water and methanol or methyl alcohol are two examples of molecules that are polar. Ethane, on the other hand, is a molecule that's nonpolar. There is no positive or negative end of the molecule and therefore is not affected by a charged wand. But polar molecules are. It didn't matter if the wand was positive or negative. We said that the polar molecules were the things that beat it up because they had really strong, we introduced the term intermolecular forces of attraction that held the molecules to each other. And the nonpolar molecules did not have strong IMFs, which is why they didn't form a bead. They just sort of spread out on the wax paper. We introduced the idea of like dissolves like, which was sort of our shortcut for determining what things will dissolve in each other. And specifically, we looked at water because that's what we focused on as our solvent a lot throughout the year. Like dissolves like means that for two molecules to dissolve in each other or to be miscible, they have to have like polarities. So that means polar substances or polar molecules will only dissolve into other polar molecules, and nonpolar molecules will dissolve into other nonpolar molecules. Ionic can be considered polar because ionic compounds have positive and negative ions, so it's like a positive and negative charge. Polar substances will dissolve in other polar substances because they both have charges to their molecules, positive and negative ends, that will sort of link up like opposite ends of a magnet. Nonpolar molecules and nonpolar molecules mix by simply just sort of falling into each other. There's no strong attraction between them. The reason why a nonpolar molecule won't mix into a polar molecule, so for the example like iodine and water here, is that the water molecules have positive and negative ends to their molecule, but the iodine molecules don't. So there's nothing for the water molecules to sort of latch onto or grab onto to dissolve the iodine in solution. We didn't name intermolecular forces by name, but we just looked at the relative strength of each of them. The most important thing is that the intermolecular force, inter meaning between, molecular meaning molecule, is that it's the force of attraction that holds one molecule to another molecule. The intra means within. The intramolecular attraction is the actual covalent bond that's holding the two atoms together, but the intermolecular attraction is what holds one molecule to another. The stronger the intermolecular force, the stronger the molecules are held together, the more likely it is to be a liquid or solid versus a gas. Some other things that we saw. We next introduced the concept of electronegativity. Electronegativity was looking at the attraction by an atom for valence electrons in a bond. So, for example, we looked at the entire periodic table and we saw that there was a trend in electronegativity, that the element with the highest electronegativity was fluorine in the upper right, lowest was down here, the lower left, and the higher value means that that atom, when it's in a bond, when it's forming a covalent bond, can pull the electrons, those two electrons in the bond, closer to itself. So the electrons will hang around that atom most of the time. So, for example, in the picture here, if two hydrogen atoms are bonding together to form a molecule of H2, because they have the same electronegativity, they pull on those two electrons in the bond with equal force, so the electrons stay directly in the middle. For a molecule like HCl, if we look in the periodic table, chlorine has a higher electronegativity than HCl does, which means that chlorine has the better attraction for those two electrons in the bond. Now, because we can have those two different types of covalent bonds, again, covalent bonds are sharing electrons between nonmetals, because the electrons can be shared equally or unequally depending on the electronegativities of the atoms, we classified covalent bonds in one of two ways. The covalent bond can either be polar covalent, where the electronegativities of the atoms are different and one atom has the electrons closer to it, which makes that part of the bond partially negative and the other side partially positive, that it's pulling the electrons away from. And we also use this symbol to represent the dipole, right? The direction the electrons are being pulled. A nonpolar covalent bond are the easiest to identify because they're the same atom. They have the same electronegativity, they're sharing electrons, but because they have the same electronegativity, they're pulling with the electrons with equal force. The electrons stay directly in the middle. There is no net or partial positive or partial negative end of that bond. If the electronegativity difference is so great, not only it's no longer a covalent or polar covalent bond, but if the difference is so great, then that one atom that has such the higher electronegativity value can actually pull the electrons completely away from the other atom, and then we're not even in covalent bond territory anymore because they're not sharing them. Then it's an ionic bond where the electrons were transferred. So the example here is sodium chloride, where chlorine has such a higher electronegativity value than sodium that it doesn't even share the electron anymore, completely rips it away from sodium. You create a full-on negative charge and full-on positive charge. That's how ions are created, and that's an ionic bond. So we summarized with a chart that looks similar to this, where we're looking at the difference in the electronegativity value of the two atoms. If the difference is zero, meaning the electronegativity is the same, that's your nonpolar covalent bond, like the Cl2 here. As you get a difference in electronegativity, right, so here's the nonpolar covalent, the electron cloud is equally distributed. As the difference grows and one atom becomes more electronegative, then the electron cloud gets pulled to that atom. You form a partial negative, partial positive. That's your polar covalent, so that would be like the HCl here. And then if the difference becomes so great, the electrons completely transfer, you're left with two ions, one fully positive, one fully negative. And that value that we gave was if the difference in electronegativity was around 2 or more, then the bond is most likely going to be ionic. That was sort of our cutoff. It depends, but our cutoff was somewhere around 2. So you should be able to identify whether a bond is polar covalent, nonpolar covalent, or ionic. The last little bit we looked at was the polarity of the actual molecule and where that comes from. So we took the idea that these bonds, the individual bonds, like the CF bonds here, and the CF and CH bonds in this molecule, could be either polar or nonpolar, but how they are distributed around a central atom determines whether or not the entire molecule is going to be polar or nonpolar. So for example, carbon tetrafluoride, CF4, the CF bonds are polar. The fluorine is more electronegative than the carbon, so in each of these 4 bonds, the fluorine's pulling the electrons up closer to itself. But because they are all the same, the bonds are all identical around the central atom, and these are distributed around symmetrically, there is no positive or negative end to the molecule because the polar bonds are arranged symmetrically. So that's really how we define what a polar molecule is. It could have polar bonds, but as long as they are arranged symmetrically around the central atom, then the pull is the same in all directions. For something like CF3H, you have these 3 CF bonds are polar. This H bond is polar because the net dipole, if you look at where the arrows go, they all flow in this direction. The net dipole, we drew those as well for the molecule, is in that direction, making this end of the molecule partially negative and this end partially positive. So that would be considered a polar molecule, which we defined as the bonds being arranged asymmetrically, meaning they don't cancel each other out. Water is an important molecule that you should be familiar with how to draw, and you should know that water is a polar molecule. It's the most famous polar molecule. And the oxygen end is the slightly negative end, or the partially negative end, and the hydrogen end is partially positive because of how the dipoles, the individual dipoles, go. Each of those bonds, the oxygen is more electronegative, so in each OH bond, which is polar, the oxygen's pulling electrons up towards it, so the net pull of electrons is up towards the top here, making that end partially negative and this end partially positive. We looked at shapes last chapter, and we tried to relate the shape that a molecule had to whether it was going to be polar or nonpolar, and we came up with a couple of shortcuts, right? We said that bent and pyramidal will always be polar molecules. There is no way to get everything around the central atom to be consistent, because there's always either one lone pair for something that's pyramidal and two lone pairs for something that's bent. That's never going to match any of the bonds that are there. But for something that's linear, or trigonal planar, or tetrahedral, that depends on what the bonds are around the central atom. So for example, in this tetrahedral molecule, because all of the atoms around are consistent, or whatever's going on around the central atom is consistent, that means it's nonpolar, it's symmetrical distribution. Everything around the central atom is not the same, so it's polar. One end is going to be partially negative, the chlorine, which is more electronegative, and one end will be partially positive. This linear molecule, HCl, obviously those two atoms are not the same. So it's easy to see why this molecule, which really is just the bond, is polar, because that end's partially negative, that end's partially positive. We related the idea of polarity of a molecule to why most molecules that we smell are polar and the ones that are nonpolar do not smell. And we took something like, for example, let's take the PCl3 here. The PCl3, its shape is pyramidal. If we drew out what the shape really looks like, if we wanted to put it in between these two charged plates, we would have to consult the periodic table to figure out which atom's more electronegative. The answer here is chlorine. So this end of the molecule is partially negative, leaving that end partially positive. And this thing, if we threw it in here as is, would actually flip itself around to look something like that, right? The negative end of the molecule is going to flip and attract itself to the positive plate, and the positive end of the molecule is going to flip and attract itself to the negative end of the plate. And that's similar. We use that idea to introduce how the molecules that we smell actually dock into the receptor sites. There were two processes that occurred here. One, those gaseous molecules they have to dissolve through the mucous membrane in our nose. The mucous membrane is mostly made of water. Water we know is a polar molecule, and going back to what we said about like dissolves like, only polar molecules can dissolve in other polar molecules. So the only thing that's really getting through that mucous membrane in the first place are polar molecules. On top of that, the receptor sites themselves have polar molecules that attract the other polar molecules so that they can actually sink into and dock into the receptor site. The nonpolar molecules are not attracted to the receptor site areas. So for both of those reasons, that's why it's the majority of polar molecules that smell and not nonpolar molecules. And the last thing we did in this chapter was summarize that exact information with this chart. We related the polarity of molecules and also the phase, which is important, right? One of the most important things was that we can only smell gases, okay? The molecule has to be in the gas phase. It could start out as a solid or liquid, but that solid or liquid would have to turn into a gas very readily if we were going to smell it. There's no smelling of a solid or a liquid. So for metallic substances and ionic substances, those are always solid at room temperature. Those never have a smell. We talked about the metals. The smell that's most commonly associated with metals actually has something to do with the oils on your skin and the metal reacting with it, and that's what you're smelling. For molecular things, we have to look at their size. The larger molecules have stronger IMFs, which makes them most likely to be a solid. So the large molecular covalent molecules, which are solids, are not going to smell either. Plastics, all that stuff. The small molecular covalent compounds can either be nonpolar, the molecule can be symmetrical, or it can be polar, which is asymmetrical. The smaller molecules are gases because they have weak IMFs, but we just said the nonpolar covalent compounds tend not to have a smell because they don't dissolve through the mucous membrane and they don't dock to receptor sites. So things like nitrogen, carbon dioxide, CH4, O2, all of that. The two things that do have a smell based on bonding are the molecular covalent substances, the small molecular covalent substances that are polar, so HCl, H2S, that's like the rotten egg smell, ammonia you smell in cleaning products, and the medium-sized molecules, which now have a little stronger IMFs than the small molecules, so it makes them a liquid. They're not as strong as the large molecules, so that's why they're in between the solid and gaseous phase. Those can be polar or nonpolar, and those have a smell as well. So the only nonpolar molecules that have a smell are the medium-sized ones. Octane, like gasoline, Carvone, which has a minty smell. So the only things that have smell that we came up with were the small polar covalent molecules and the medium-sized polar and nonpolar covalent molecules. The reason why the medium nonpolar covalent molecules have a smell, and the reason they can get through the mucous membrane and dock to the receptor site, is that because they are larger, their intermolecular forces are a little bit stronger, and they have a better interaction with the mucous membrane and the polar receptor sites. There's one more summary table I gave you on the bottom here that related all of the bondings: ionic, metallic, network covalent, because those are all solids at room temperature. Those things never, ever, ever have a smell, but it's the molecular covalent things that do. We just have to double check the size of the molecular covalent substance, and then after we check the size, whether it's polar or nonpolar, to make a determination about whether it's going to smell. And of course, the most famous polar molecule, water, doesn't have a smell, and we talked about that as well. And one of the hypotheses is that, well, we have so much water in our body and in our nose that we're exposed to it all the time that we wouldn't recognize the smell even if it did have one. That brings us to the end of Chapter 8 and to the end of Unit 2, Smells.